In this lecture, we're going to see how you can build your own concepts. And this is going to bring us into the second part of concepts we can use in C++. In the last lecture, we used the concepts from the standard library that are built into the C++ programming language starting in C++20. In this one, we're going to be building our own concepts. And without waiting anymore, let's see how you can do that. And this is the syntax you can use to do that, and it is really simple. The way you do that, you say a template declaration specifying the template parameter you want to constrain, and then you say concept. You say the keyword concept, you give your concept a name, you put the equal sign after that, and then you're going to specify the requirements for your concept. So for example, here we are using a type trait to specify that this type trait is going to determine what works for this concept here. And what this is going to do is to enforce for our template parameter to only be integral. If it's not integral, we're going to get a compiler error. And one thing I should tell you is that the std integral concept is exactly built like this in the C++ standard library. This is really cool. So if you want to set up your own concept and you want to do that using type traits, you can do that like this, and it is going to enforce for your template parameters to satisfy that type trait. Or to be exact, the concept is going to be satisfied when the type trait evaluates to true. If the type trait evaluates to false at compile time, the concept is not going to be satisfied. That's another way to look at that. Down here, we have another syntax we can use if we have multiple statements in our concept. All you have to do is specify the concept keyword. You give it a name, you put the equal sign, and then you add a requires clause. The requires clause is going to specify the template parameters for which you want to enforce your concept. And then you're going to put a pair of curly braces, and inside that, you're going to specify the syntax you want your concept to satisfy. For example, here we want for the two parameters to be supporting the multiplication operator. If this multiplication operator is not supported for the template parameters that we pass, the concept is going to fail. And again, I should emphasize that this doesn't check for the value of a multiplied by b. It's just going to enforce for the syntax to be supported. So for example, if you call a function template with this concept and you try to pass in integers, it's going to work because you can multiply integers. But if you pass two strings, this is going to fail because it doesn't really make sense to multiply strings. Okay, this is the syntax. Now we only have one statement to enforce inside, but if you want, you can even put more statements. If you go down here, we have another example called incrementable. This is going to require for the template parameter to be incrementable. We specify the concept keyword, we say the concept name, we put in our equal sign, and then we say requires, we put on template parameter and put in our requirements. For any template parameter that is using this concept, the syntax here must make sense. So you must be able to take the value that you get from here and, for example, say I plus equals 1. This is going to be valid syntax. You're going to say plus plus a and plus plus b. All these are going to be valid C++ syntaxes for the template parameter that you try to call this function template with. And if this doesn't work, you're going to get a compiler error because your template argument isn't really satisfying this concept. So this is really how you can set up your own concepts in C++. Once you have your own concepts set up, you can use them like we have been using the other concepts from the C++ standard library. For example, we can use syntax 1 to put a requires clause and say that we want to satisfy our own concept. With this particular syntax, you will have to put in these angle brackets and put your template parameter inside. This is the syntax you have to use. You can also use syntax 2 and specify my integral directly in these angle brackets in your template declaration, and this is also going to work. We can even use this with the auto syntax for our function templates. It is going to work. Okay, now that you have seen this, I think it is time we headed over to Visual Studio Code and played with this a little more. Okay, here we are in our working folder. The current project is building your own concepts. We're going to grab our template files like we always do, and we're going to put them in place. And we're going to open this thing in Visual Studio Code. Let's do that. We have our project open here, or folder, I should say. We're going to clean this up a little bit, and we're going to include our concepts library, and we wanted to set up our own concept. The first syntax we're going to see is by using type traits, and we're going to say template type name t, and we're going to say this concept we want this template parameter to satisfy. We're going to say concept, and we're going to say my integral, which is going to be the name of our concept. We're going to put an equal sign, and then we're going to say std integral v and specify that we want this type trait to be satisfied for this concept here. And after this, we need to put in our semicolon, and I think we need to include the type traits library because we are using that. We should say std is integral. So sorry for that. And this is going to work now. Okay, now that we have the concept set up, we can use it like we have been using other concepts. For example, we can set up a function which is going to add up two numbers, and it is going to use this concept here. We have multiple syntaxes we can use. So let's go down and try this out. We're going to say template and say type name t, and we're going to require this concept to be satisfied for our function template. We saw that we could use the requires clause here and say my integral and say the template parameter we want to enforce this on. And after this, we're going to just put in our function template. We're going to say add. What we have been doing all along in the last lecture, we're going to say ta and tb, and we're going to return a plus b. Now, this function is going to support our concept. Let's go down and set up two variables. We're going to say int x, and we're going to say 6, for example, and int y, and we're going to make this a 7, why not? And we're going to say add x and y. Once we do this, you see that we have no problem because the concept is satisfied. For the arguments that we are passing in here, the concept is satisfied because the type trait here is going to return true for this type here because it is an integral type. When the type trait returns true, then the concept is going to be satisfied. If the type trait returns false, the concept is going to fail. Let's try and build and really drive this home. You see that the build is good, our function is working. So the function template instance for this call here is going to be successfully generated, and we're going to call it when the program runs. Now, let's change the type of these guys to double and try to violate our concept and make it fail. Once we do this, you see the call here has a squiggly line, and Visual Studio Code is not going to say that it is a concept problem, which is a shame, but we can still run this through the compiler, and the compiler is going to tell us what is wrong. So it's going to say use of function add with unsatisfied constraints. And if we go down, we're going to see the exact constraints we violated. And we're going to say required for the satisfaction of my integral with t. We are calling this with double, and double is going to evaluate this to false. Hopefully you can see that you can really set up your own concepts using this syntax here. And we can use our concept with all the syntaxes we have seen in the last lecture. So for example, we can take out the requires clause altogether here and say my integral in the template declaration here. So we're going to say my integral. And if we do this, we're going to fail again because the concept is not going to be satisfied. We're going to have the same problem. We can change the syntax to use the auto syntax, but before we do that, let's change this back to type name t, and then put our requires clause after the parameter list of our function template. We're going to say requires, and we're going to say my integral, and specify the template parameter. And this is a valid function template with a concept applied to it. And if we build again, we're going to get the same compiler error. So you see the same error. And we can use the auto syntax. Let's do that. We're going to take out the template declaration here. We're going to take out the requires clause here. And we're going to change our t to auto. And the way we do that, we're going to say std, no std. We are using our own concept. So we're going to say my integral auto. This is going to work. And we're going to say my integral auto and my integral auto here. The moment we do this, You see that we have squiggly lines here because our concept is violated. But if we try and build again, we're going to use GCC to do that. The build is going to fail. You see that the same concept is violated. And we are able to use our concept throughout the 4 syntaxes that we saw in the last lecture. And this is really cool. Now that we have this, we're going to comment this out. And we're going to see that we can set up concepts that have requirements spanning multiple statements or multiple lines. Okay, let's go down and do that. Suppose we want to set up a concept that is going to enforce for the template parameters to be multipliable with the multiplication operator we have here. We can use this syntax here. We're going to put in our template declaration. We're going to say concept. We're going to say the concept name. We're going to put in an equal sign. And then we're going to put in a requires clause with our template parameters n. And after that, we're going to put a pair of curly braces. And inside the curlies, we're going to put the requirements. For example, in this case, we require for the template parameter here to support the multiplication operator between 2 of these types. If the multiplication operator is not supported, we're going to have a problem. And this is the concept that is going to enforce that. One thing you should know is that this is just going to check that multiplying A and B is valid syntax. It's not going to check the value of A multiplied by B, and you should really understand this. Now that we have this n, we can set up a function to use these 2 guys. Why not use the function we have seen before to add 2 numbers? Let's do that. And we're going to put in our requires clause, and we're going to require now to support the multipliable concept, and we're going to specify our template parameter. We have the concept n, so we can use that to do whatever we want. Now we're going to say t add, and we're going to say ta and tb, and we're going to return a plus b. This is the same function we've been using all along. Okay, now we have our concept in place, and we have a function template that is going to use this concept. Let's see if we can add up x and y and see what we get. We're going to build with GCC. We're going to see that the build is going to be good because our concept here is satisfied. We are passing double types for our function template, and it is legal to multiply 2 double variables. If we multiply 2 doubles, we're going to get a value, and that's going to be valid C++ syntax. But let's see what happens if we try to change our arguments to std string. Let's do that. So we're going to say x is hello, and we're going to say y is world. Why not? Let's go down and put in our semicolon. And the moment we do that, you see that we have a problem. And Visual Studio Code is not good at this yet. But if we go inside and run this through GCC, we're going to get that our concept is violated. Let's look at the compiler error here. It's going to say constraints not satisfied, and it's going to tell us that we are calling the add function with values that can't be multiplied. It's going to say the required expression here is invalid. And this is how you can set up a concept like this. And you can really use this to put constraints however you want on your function templates. But here we have just used one statement inside our concept here. We can even put in more. So to drive this home, we're going to set up another concept. Let's go down and put that in place. The concept is going to be called incrementable. It's going to be using the same syntax we saw here, but we're going to be putting a requirement on the template parameter here to support incrementation. And we want for every type that goes in the place of t here, we must be able to say a plus equals 1. This must be valid C++ syntax. We must be able to say plus plus a. This must be valid C++ syntax. And we must be able to say a plus plus. This must be valid C++ syntax. Now that we have this, we can change our add function to use this concept. Why not? We're going to say incrementable. And now this function is going to be required to use things that we can increment on. And you see it is failing already because we can't really increment strings. What does that even mean? So let's build and show you the compiler error. Okay, you see incrementable is not satisfied and the required expressions aren't valid. You see plus plus a is not valid, a plus plus is not valid, and a plus equals 1 should not also be valid, but we're not seeing that here. But hopefully you see the message here that our concept is failing here. If we comment out our strings here and uncomment double, all these operations we have here are supported for the double type. So we should not fail here if we try to compile this, because the concept is going to be satisfied. Let's use the GCC compiler to build. You see the build is good now, and we can clear and we can bring up a terminal to really see this, that our binary was generated. Let's do the IR. We're going to see our rooster executable here, and if we go down, let's say done, we're going to see that if we build again to bring this in consideration, clear run rooster, the program was generated and it is really running because the concept here is satisfied with our call using double arguments here. Okay, so this is really all I set out to share with you guys in this lecture. I hope you know the syntaxes you can use to create your own concepts. You can either use type traits like we have seen here, and the syntax is to put the keyword concept, put in your concept name, put an equal sign, and then specify your type trait here. This is going to work. If you need something a little more complicated, then you're going to use this syntax here and put the requirements for your concept in these curly braces. You can either put one statement like we did here, or you can even put as many statements as you want. Just remember to end them with semicolons. And another thing you shouldn't really take lightly is that this is just going to check for syntax. It's not going to check for the value you get after you add 1 to A here, for example. It's not going to check for the value you get after you multiply B. It's just going to see that A multiply B is valid syntax for the types that our template parameter is using here. We are going to stop here in this lecture. In the next one, we're going to zoom in a little more on the requires clause here. Go ahead and finish up here and meet me there.